Thank you, Xiaonan. Good afternoon, everyone. My name is Xiaodong from Eversource Energy, and thanks to UNIFI for providing this opportunity for Eversource to share Eversource experience on grid forming technologies, the grid forming STATCOM and grid forming battery. Both devices have been in operation Eversource, and both are the first kind of in US. So I will present the STATCOM first, and thanks my colleague Li Bao, who is also in the call, for providing many simulation diagrams in the presentation. Ling Yang, my another colleague, will present the grid forming battery after my presentation. We definitely welcome questions from audience, so we'll try our best to answer questions after the presentation. All right, let me start by introducing Eversource first. Eversource is the largest utility in New England with 4 million customers across the 3 states in the Northeast. Eversource owns and operates almost 50% of ISO New England transmission network. At the distribution level, Eversource serves 50% of ISO New England load. Regarding renewable, the DER, there have been 4 gigawatts DER online in Eversource service territory, and another 3 gigawatt DER, which almost 20,000 projects are waiting in the queue for the Eversource to prove it. In addition, Eversource has been investing renewable energy resource projects, including the battery and the offshore wind. And 2 of the projects are significant that we're talking about today, because both projects deployed grid forming technologies to improve the resiliency and reliability of the grid. One the project, you can see that 25 megawatts battery, right here, right? And the other one is grid forming STATCOM is located onshore substation of the offshore project, New York Long Island Rail. We can see the next slide. Right, on the right, it shows the location of battery projects. The battery has been operating since 2 years ago. The area below, let me highlight it. All right, this one is leasing area, offshore leasing area. So the Block Island, the offshore wind, the blue line here, the close by, is first offshore wind in the federal waters. And there are another one, the red line. Red line is South Fork wind, went into operations in the March of this year. So it's onshore substation right here. Located in the East Hampton, installed 75 megawatt grid forming STATCOM, and has been operational since October last year, that's 2023. From the broad view of the station, you can see that the STATCOM building is a major part of the substation, occupying a very large space. I will focus on discussing the STATCOM. Interestingly, you can clearly see that the grid forming battery and the grid forming battery are all installed at the remote end of the island, the remote end of Cape Cod and the remote end of the Long Island, and both grid are weak grid. All right, so this is simplified one line of South Fork wind, which consists connect to a Long Island 69 kV network with 130 megawatt generation. The export cable here is a 138 kV, 60 miles long, and it connects to the secondary side of a 3 winding transformer. The STATCOM right here is connected to the 24 kV tertiary of the 3 winding transformer. The STATCOM is basically positive, negative 75 megawatt with overloading capacity up to 84 megawatt for 3 seconds in inductive mode. In the preliminary design of the South Fork wind, the multiple options were evaluated to compensate the large charging of the export cable. The options include the reactors, the fixed reactor, variable reactor, STATCOM, condenser, or combination of these devices. In the very beginning of project, right, very early stage, it's very normal that many parameters are unknown or at least are not accurate at all. However, the factors below are critical and must be roughly assessed, including the reactive power and the power factor requirement API. Many utilities normally require positive, negative 0.95 power factor, and the photorized performance requirement, including the overvoltage, undervoltage, overfrequency, underfrequency. Utility is different, so they normally have a different requirement. And now we have some standard from REE, P2800, and the coming, the PRC 029. These requirements are important because these requirements affect not only the selection of device type and the protection settings, but also the physical size, the cooling system design. For example, the GSU of STATCOM and condenser are affected by frequency write-through requirement. Also, other important requirements like the voltage dip and the megawatts spillage, during contingencies and project energizations are important. That should be considered as well. All these requirements are used to determine the device type, the size, the dynamic voltage regulation capabilities. Also, the delayed current zero is another big concern listed here. It's very important in AC offshore wind and must be mitigated. We can discuss later. So of course, the space and the cost and must be respected as well. Based on the requirement, the STATCOM was eventually selected for the solution of South Fork wind. Then the question is, why the grid forming STATCOM instead of a conventional grid following STATCOM? We know that the STATCOM can be installed with different controls. The conceptual diagram here, the grid following STATCOM and the grid forming STATCOM, I think is pretty well known. So the grid forming control strategy STATCOM is that the converter behavior like voltage source behind the impedance. One thing important to note is that the STATCOM synchronized with grid based on the active power mismatch between the STATCOM and grid. So this behavior of the grid forming STATCOM. So it does not rely on the PAL. We know this is the same behavior of the traditional generator synchronized with the grid. And also its response is very fast. It helps the South Fork wind connecting to the weak grid, that is the far end of 69 kV network of the Long Island, and achieve very fast synchronization and very stable operation. When there are fault, it also improves the fault write-through performance of one farm. Another advantage of the grid forming STATCOM is that it produces a good amount of negative sequence current, right? So especially on the unbalanced fault, right? This helps the protection, to recognize the fault type and locate the fault. More importantly, it also helps to resolve the zero miss issues for a dozen of contingencies in South Fork wind. Additionally, this voltage source behavior has been found to be useful to mitigate the TOVs, that is the temporary overvoltages. All these distinct features of grid forming control help the South Fork wind successfully integrating into a very weak grid. This slide I want to show an example of a grid forming STATCOM responding to a frequency change. The capacitor cells in the STATCOM can discharge and absorb the energy and inject active power or absorb active power. And you can see the DC voltage, DC lag voltage changes with the frequency change. This behavior is not observed in the grid following control strategy. We know that some manufacturers have developed a so-called enhanced STATCOM, STATCOM, since I think 2021. And the STATCOM uses supercapacitors to store much more energy and achieve a much better performance. Based on some studies that the STATCOM can provide inherent inertia, which is 10 times larger than the same size of condenser. That's a really amazing technology advancement. The grid-forming STATCOM in South Fork Wind had the same control as the STATCOM, but a little bit reduced frequency supporting capability, but it's still good. So with the grid-forming STATCOM in operation in South Fork Wind, Eversource has been starting to explore potential application of enhanced STATCOM in Eversource system. On this slide, I want to show you a comparison between the grid following and the grid forming STATCOM. The first diagram is the STATCOM response on the step change of grid voltage. It can be observed that the reactive power response of grid following is slower than the grid forming. The second diagram shows the STATCOM response on the 10-degree phase jump of the grid. And the third diagram right here shows the response of 0.5 Hz frequency drop. So it can be clearly observed that the grid forming STATCOM react the phase jump and the frequency drop and absorb the active power up to 25 megawatts for this 25 megawatt size of STATCOM. So there's no active power response. You can see from diagram from the grid following STATCOM. And so this simulation confirms the voltage source behavior of the grid forming STATCOM. This slide will compare the stability performance between the grid forming and the grid following STATCOM. The first diagram here shows that on the line outage scenario, and the grid is super weak when there are disturbance from grid, and slightly reduce the short circuit capacity a little bit more, the wind farm become unstable under the grid following control of the STATCOM. You can see that the wind farm become uncontrolled, growing oscillations, right? The grid forming STATCOM instead, right? The grid forming STATCOM, the origin line, can effectively make the system stable. This showed better small signal stability performance of grid forming over the grid following, right? The second diagram here on the right shows the fault ride through under extreme contingency, right? The South Fork Wind cannot ride through the fault under the grid following STATCOM, right? But successfully ride through on the grid forming STATCOM. This improved the stability performance. The grid forming control helped the South Fork Wind avoided many limited operations. That is, avoided generation curtailment in the line outage scenarios when the system is weak. All right, just as a test, and we replaced the grid following STATCOM with the STATCOM and try to observe its response, and it showed even better dynamic stability performance. Let me show you here, right? The red line, right, in the first diagram. So the oscillation mode of the grid forming STATCOM and the grid following STATCOM is almost completely suppressed in the enhanced STATCOM. So you can clearly see from here. Just a test. All right. All right. So what about the STATCOM performance during a fault? That is what the short circuit contribution of the grid forming STATCOM. This question is important for protection. From the example here, 7-cycle single-line ground fault, you can find that the grid forming STATCOM contribute a good amount of negative sequence current. It's good for protection. Also, its voltage source behavior counteract the voltage changes, which is similar to a synchronous machine. So on the unbalanced fault, the grid forming STATCOM intend to increase the positive sequence voltage while decrease the negative sequence voltage. So the traditional grid following STATCOM doesn't contribute any negative sequence current, as we know, unless it is specially designed with a current boosting capability. However, the grid forming STATCOM inherently has a feature to improve the fault, has a feature with improved fault resistance performance. All right, so one main drive, as we mentioned, of selecting the STATCOM for South Fork Wind project was that the significant delayed current zero issue was discovered in the project, and the grid forming STATCOM helped to resolve the issue. All right, so as I mentioned previously, the 138 kV export cable is 60 miles long, which is has a very large charging. So the project was initially designed with the largest reactor to compensate the larger cable charging. However, as shown in the diagram, when there's a fault either on the grid side or on the export cable side, the fault current have a larger DC component, which makes the current fault current miss the current zeros in many cycles, as example here. So the breaker cannot interrupt the fault, cannot open, right, after 4 or 5 cycles. So this will result in break failure, right? The zero miss issue is the worst when the energized export cable into a fault. The issue must be resolved in order to safely energize the offshore wind farm. Then the project modified the design and replace 50% of the reactor with the STATCOM and resolve the zero miss issue, because the STATCOM contribute AC short circuit current and does not generate a DC current component. From this point of view, the STATCOM are even better than the SYNCOM. From a diagram right here, you can see that the installation of STATCOM increase the short circuit current, and the short circuit current across zeros within multiple cycles of the fault, right? Which means the line breaker can safely interrupt the fault and resolve the zero miss issues. All right, the STATCOM model. The STATCOM model need to be validated. The model validation is a long process, starting from the factory test to the site test until months after commercial operation of the project. The FAT RTDI test, that is a hardware in loop test, is the first step to validate the STATCOM controller model. It provides the opportunity to identify issues, adjust the controls and the protections between the hardware packaged and shipped to the site. However, remember that the FAT test is limited. It's limited by controller and the protection hardware only, not the STATCOM equipment itself. And the grid model, the wind farm model, are highly simplified in the RTDS because of limitations of the simulation platform. The SAT test, that is site test, is the best opportunity to demo our wind farm devices, one-by-one devices, or as operate as a whole, right? Operate as expected on the different operation topologies and changeovers, including single device switching, energization, control step change, control mode change. All measurements are recorded and compared with PSCAD simulations and the South Fork site test. If there are differences between recorded data and simulation, investigations would be performed. On the right, I just show you an example of PSCAD simulations and measurement comparison on the capacitor switching event. The wind farm and the STATCOM response closely match the measurement. So this kind of simulation helps us to gain confidence with the PSK model. There are some other tests, the complex test. Complex test to confirm that the wind farm meets all kinds of technical requirement set by NERC, ISO, TO, or interconnection requirement. The reliability test is also very important to verify the reliability of the wind farm over extended time period. For example, 200 hours continuous operation. We know that there are plenty of things which can't be modeled. For example, the cooling system of STATCOM. So it is important to know its performance and if it's operated reliably, right? The disturbance and rejection test is also important. It's normally carefully controlled and it's required, right? It's good. It's good to test the project response on the largest disturbance. Now, again, it's very valuable that to compare the PSK simulations against the field measurement. All right, so what did we learn from a grid forming project? Okay, there are many experiences and lessons learned. I summarized a couple of study-related items here. First of all, one experience is there's no plug-and-play model. There's no single model and control parameters for manufacturer can fit all applications. That means when receiving a model from manufacturer, extensive screening studies must be performed to determine the suitable controls and protection, even with the minimum knowledge of the grid and the detailed wind farm parameters. The preliminary study should include the step test, voltage step test, right? Function step test, phase jump, and the different fault, which are closed STATCOM. The STATCOM response time, the overshot, settling time, over voltage, over current, and so on, should be compared with the different control parameters, like controller gain, slope, protection settings, to make sure that the STATCOM meets the basic performance expectations and stable and no voltage and exceeding installation level. So manufacturer's default model has never been plug and play. They always have something to be adjusted before more detailed studies to be performed on actual system. At the screening and the preliminary study stage, normally a range of control parameters are determined, which will save you a lot of time in the following study. For example, the diagram on the right, show your STATCOM will be unstable in the weak grid with a controller gain in a certain range. And this range should be avoided in the following studies. Not ideal performance for the model should be discussed with the manufacturer to get it resolved, the sooner the better. One lesson learned from the STATCOM project is that the STATCOM has a different operation modes, right? And all operation modes might be studied at a different grid strengths, grid contingency, farm internal contingency, and a different farm output. For example, the diagram below shows STATCOM's response, right, on the grid event, the reactive power control mode, right? That's the one control mode we overlook. The STATCOM does dampen the high frequency oscillations, right? You can see it's going down the oscillations, right? But it's not good enough to meet the performance requirement that is at least 30% of damping ratio for any oscillations. So this scenario was unfortunately overlooked in previous studies. So we have to go back and restudy scenarios, discuss the major factors, and get the control code improved by adding a low-pass filter and improve the damping ratio from 1% to 9%, and install the new code at the site. Take actual effort, right? All right. The third one, the lesson learned, no matter how good the STATCOM shows in the studies, as I just mentioned, the plenty of things can't be modeled. PSCAD model is not everything. One example is during the side test of the software wind, right? A power quality issues in the grid failed the variable frequency drive, the so-called VFD device, in front of electrical motors of the STATCOM's cooling system. So this VFD device failure caused the STATCOM's cooling system shut down. So STATCOM tree and the wind farm tree. So this event highlighted that the importance of the side test for the extended time period when the system and the grid experience the high load, low load, different switching, and maybe many unexpected event. The STATCOM performance must be validated against this real-time grid conditions. The last item, realistic grid modeling, what I want to show is that although the planning study intend to be conservative, over-conservative assumption not good may lead to not only unnecessary cost of the wind farm, but also unrealistic system response and issues which can't be mitigated at all. Let me show you the next slide. All right. Just before the commissioning test, a study showed that the South Fork wind, the STATCOM, and the wind farm will be unstable upon a double circuit contingency at a light load contingency. This will result in a significant generation curtailment at pre-contingency, which is unacceptable for the farm. Unfortunately, further studies revealed that the instability only occurs when the motor content of grid exceed 50% of total. All right, but in reality, the motor load content is only about 20% per information given by the local TO. So this is far below the stability threshold of 50% of motor load. So what happened was in our previous studies, the load was assumed constant PQ load. We know that represents the 100% motor load. As shown in the diagram on the right, the system is unstable at 100% PQ load. So our previous studies and assumption was just too conservative and unrealistic. So we had to go back, restudy, correct the previous study result, and the system showed stable at 20% PQ load under all contingencies. All right, that's all I have today for grid forming STATCOM. Thank you very much. Hand it over to Lin to present the grid forming battery in Eversource.
Perfect, great. Maybe Xiaodong, you can stop sharing and Lin can start to share her screen.
Yeah, thank you, Xiaodong.
Yeah, perfect. Lin, I can see your screen. You probably want to go to the presenter mode.
Okay.
Yeah.
Yeah. Thank you for the invitation. And my name is Lin, and happy to be here to share our grid forming battery storage projects at Provincetown with everyone here. This is a brief agenda, the overview of the projects and some of the system studies, and also want to share some of the post-commissioning the system performances. The beginning, the project overview, the drivers and implementation changes. The value of the project and the project back in 2019, and I think the Mass DPU approved our proposal to demonstrate the grid, the microgrid and pilot projects in Provincetown. In historically, our distribution circuits supply the area here has been a poor performing circuits. And the engineering department proposed the solution to deploy the microgrid to list certain circuits, distribution circuits with the battery storage system to be the solely supply for the area. The battery storage combined with these microgrid applications, it will allow us to defer a transmission supply and as well as a distribution line in the area. There are quite a lot of projects to bring the projects from concepts to reality. Just want to show some pictures, and this is like the concept of the battery plants, and this is the actual site of the projects, and the use cases including the voltage supports for the blue sky day and the islanding, and as well as peak shaving under certain system conditions. This is the project statistic of the site, and we have a building for this battery, and the building size is greater than 10,000 square foot. The battery size is 25 megawatts and 38 megawatt hours, and we use the lithium iron battery. Depending on the circuit loading, solar charge time and the discharge time is really depends on the circuit loads, and the life cycle of the battery is 12 years. We have in total like 16 inverters and many battery modules and racks, and we also have like a 2 grounding bank for the site. So this is the statistics of the projects. Aside from the battery sites, we have done a lot of like system upgrades along the distribution circuits, and we have installed new like reclosers and with the automatic switches, and also we have done some like a substation upgrades. Under certain circumstances, we require the system to be tripped faster to avoid some system stability issues. And as well as the communication infrastructure upgrades in the area. In total, we serve about like 10,000 around like 10,000 customers along the distribution circuits for the battery interconnects. So those are some of the pictures from the field. I'm not going to like talk about it, but just kind of like show what it kind of look like and from the field. And some of the exteriors includes the step-up transformers and grounding bank. Design challenges. We meet a lot of like design challenges. I wanna actually like talking about this one first. So first of all, this is like one of the first kind and projects, and this is the first microgrid project for Eversource. And for the inverter and the grid forming inverters and the control inside it is kind of like a black box. That's kind of very new to us. And also during the design phases and how we ground the systems. And at the very beginning, we found out there were like affected grounding and transient over voltage. And we spent quite a lot of time on trying to mitigate the transient over voltage. And the system is very the point of interconnection is a very weak system. It's almost at the edge of the system. So we identify like stabilities like early stage of the studies. So how we make sure and how we tune the parameters and make the system stable. Aside from that, and the protection and control is also another beast. So there are quite a lot of like challenges along the way when we design the project. Oops. Here give you an overview of our system. I'm showing like two substations, substation number 1 and the substation number 2. Those two substations are 115 kV to 23 kV distribution station, and the battery storage is interconnected about like 13 miles from the source substation. It's almost kind of like at the edge of our system. And not only that, the source station is connected through just one 115 kV transmission system. So overall, the system at lab, the substation is also radially fed by the transmission system. So overall, we have like a very weak kind of like the system stiffness is relatively weak at that area. And the distribution the distribution feeder that the battery interconnects to is about like 13 miles. And we have the load like very quite a lot of load at the end of the circuits. At the end of the circuits, it takes up about like 50% of the overall circuit loading during the system peak load day. So when we propose these projects, and the primary use case of the battery is the islanding, because of the configuration of the circuits, basically if there is any like distribution faults along this feeder 3, there is no other backup supply in the area. So the primary use case of this battery is to serve as the in the distribution fault and serve as the supply source for the island. And the other use cases is under the blue sky day, and the battery will provide voltage supports. The third one is there is a because this substation is supplying by a radio 115 kV transmission line, and in case of these transmission contingencies, we also going to use this battery to perform the peak load shave, because under these transmission contingencies, all the load of these 3 feeders will be picked up by the feeder 1. So those are kind of like a primary use cases of the battery. When we design the battery, we intentionally oversize the battery to allow for the fault detections under the islanding conditions. So the size of the battery is higher than the peak load of the island. And also, given the point of interconnection is really far away from the substation, so the overall short circuit ratio at the point of interconnection is very low. So it connects to a very weak system. This kind of like provides some of the schematic of the battery sites. This is the 23 grid, the grid. We have like basically like 2 symmetric bus at the side. So this like through the battery cells and through the inverters and step-up transformer, and in between the step-up transformer to the POI, we also have like each part have like a grounding bank. At the early stage, as I said, we encounter like quite a lot of like system instabilities, and we spend a lot of time like tuning the inverter control parameters, and also we kind of like play with the grounding bank impedances and configurations, and trying to make the system be stable, and also and also making sure the system is effectively grounded. Some of the parameters that we kind of like change, trying to optimize, not only but includes the Drew settings, and as well as this like a virtual impedance mode. The virtual impedance mode is once the inverter goes into the sense there's a fault in the system, and it goes into this like virtual impedance mode. And this mode is activated by the inverter currents, and it's deactivated by the terminals of the voltage. So its activation and deactivate is controlled by different parameters. And some of these settings at the very beginning, the OEM, the manufacturer is not opening up, and they have like a default settings. So we have like working with the inverter manufacturer quite a lot through the process, and the model and some of the control parameters, they have to like open up and customize for our design. This is kind of like showing with the frequency Joule settings with like different settings, and you may notice system performances like being different. So on the left, those are the Joule settings in the early stage, and this is the performances that later on we kind of like change the frequency Joule setting. You can notice the system performances differences in between two settings. Also, the system voltage and the fault conditions, it was like all over the places previously, and later on we have like a change the voltage droop settings and trying to slow down the inverter controls. So I think under the weak grid conditions, through our simulations, we find out by reducing the voltage and the frequency droop setting, it can help maintain the system control and stability. Yeah, this is something this is also some of the system performances by kind of like tuning the different control parameters with our model and getting different results. So as I mentioned, the inverters will goes into this virtual impedance mode if it senses there's a fault in the systems, and there are like a current thresholds that allows the inverter goes into that mode, and the voltage and the terminal voltage will deactivates the mode. On the left, we notice not only like reviewing the voltage, but we also actually goes into the code of the through the simulation results, and there's a code that indicates if the inverter has go into that virtual impedance mode or not. We identify that the inverter has been kind of like a cycling in and out of that virtual impedance mode. So we kind of like reached out to the OEM and trying to understand and tuning the parameters and with like a different current thresholds with the improved system performances. With the as I mentioned before, in the early stage, we also sense that under several scenarios, the we also identify like a transient over voltage and high, like a high voltage during center under center light to ground faults, and at last scenarios, we in the previous models and we identified like the maximum system voltage would be above like 1.4 per units, which is not as not acceptable. And we with the new model, we were also able to define and set the four outputs with like different parameters, and with that updates and under the new model, and we are able to like adjust the full contribution of the inverter. On the top, the this diagram is kind of like showing the code on the left. It indicates the inverter like operation mode. Like for our cases, this like a 501 represents like a normal operation. So for this one, the for in the previous, like before we are adjusting the parameters and under circumstances circumstance, the 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 inverter may not sense there's a fault in the system, and it remains like a normal operation, but it could potentially like push its output to like a 1.8 per units of its normal rating. And by adjusting the threshold of the virtual impedance mode and under the set like the same location and same fault, and the inverter will be able to sense the fault in the system and goes into the virtual impedance mode. And under that scenarios, and it outputs like 1.2 per units um, for currents. And by reducing the current contributing from the inverters, and we were able to like reduce the transient overcurrents under circumstance. This is just like one of the scenarios that we form an island, and then the BESS is able to constantly produce P&Q and supporting the island. Through the simulation, some of our lesson learned is, and I think this is also echo what Xiaodong mentioned previously. There is not just like cookie cutters, and especially for the projects, and each of projects has like different characteristics, and especially with the system connects to like a very weak systems, and the stability could be one of the concerns. And in order to optimize the system performances, we have to like do a lot of simulations and to optimize the system performances. And sometimes it may not even have to like work with the manufacturers to open up like more parameters to be enabled for basically customize the design. I'm not a protection control person, so I'm not going to like really talking about the protection control. I leave the presentation here is I know like our protection control team has spent times of efforts to do the RTDS testing, and like have performed a lot of like scenarios and simulations to making sure that the protection devices is properly designed on the in the field. One of the design parameters want to highlight here is that we design a system that the battery is able to restore the system within 1 minute. So within 1 minute, we require the island to be formed. And for the control, and there are like different levels of control of the system. There's like a distribution system, street level control, and the microgrid controllers and the BESS, the plant controllers. And also, so there are like different levels of control. And addition to that, there are we I believe the system we also have like a different sets of controls by um, mining the condition of the system. And when the system is under the a minus zero, it's a set of control. And if it's under the a minus one, the islanding, it's a different sets of control. So there are like different sets of the control parameters has been implemented, and the system and will sense the grid condition and implements different protection schemes to the system. This is the slides our system engineering group has been put together and showing some of the system operation and post commission the system performances. After the battery has been in services, and there are several faults like happening in the system, and also the battery kicking to pick up the load during a major events in last December. Right here, I'm going to show you the battery, how the battery has been improved the customer minutes interrupted index during some of the distribution fault and also during last year's storm. In May last year, there was a fault happened near the supply source station, and the battery has been carried the customers almost like 9,900 customer for 42 minutes. This is the schematic of the supply station, and this is the distribution supply, and here is the battery station. As I mentioned, and this is a 13 miles distribution circuits, the 23 kV distribution circuits, and the majority of the load is almost right here. About like a 50% of the circuit loading is right around like where the battery is. So back in May last year, there's a fault happened somewhere near the source station. Within 1 minute, the battery was able to carry the load from almost here towards the source station. Only the customer being impacted is somewhere after the recloser has been opened. And so we are successfully pick up like more than 9,900 customers. And only like a small amount of customer being impacted during the fault. This is the actual high reading of the battery state of charge during the events being happened. For our design, we trying to maintain the battery high state of charge as possible. Like I said, the battery, we have like a BESS 1, BESS 2, and each part is kind of like equally designed. And this two lines shows the state of charge. It was about like a 94% state of charge before the event happened, and it dropped to somewhere around like 90, 92, 82, 81, 82% after the event has been cleared. And then the state of charge of the battery start to charging with resistance and slightly charge with resistance and with the state of charge going up. This is the another applications that battery has been kicked into support during a major winter storm last December. The first fault is happen in between this recloser and this recloser. So the battery quickly form island at the point of interconnection. And the unfolded circuits, like south of the circuits, is being picked up by the source station, and the four is being isolated, and the battery was able to pick up all the customer down in the Provincetown. During the major storm, and it's not like unusual that the fault can happen in series. Let me show this one. This slide deck is kind of like showing how the state of charge change during the storm event happened. Like I said, that we trying to maintain the state of charge of the battery as high as possible. So it's starting around like a 94% state of charge, and start like a discharging. Let's see. And the battery like start to like discharging, and somewhere the kind of after the first events, and then I think the battery system has been weighed up, has been weighed and then being recharged. The operators has been connected the BESS resync back to the system and charge again. And then the following fault is, and because of the following faults, and the battery starts to like discharge again. And I know like during that day, the I think one of the lessons learned from this event is that during the battery and trying to charge with the system, and the charge rate was kind of like too fast, so that we have to basically have like a half of the plant charge, and then waiting and then the other half of the battery plants be charged with the system. And through the operations, and there are some like parameters, and we have to be like optimized. And also during the faults, and when the battery trying to sync back to the system, and I believe one of the voltage regulators along the distribution circuits has like a the one of the phase of the distribution circuits, the voltage regulator tab has been stuck, and there was difficulties for the battery plants to resync back to the system. So that's kind of like some of the real operations problems that we potentially can encounter in the real world. During the simulations, and we and the like the start phase and some of the distribution, the real problems we will not like really simulate in the simulation. But when you operate the plants, and there are like different kind of conditions and can be happen in the field.
Ling, so sorry for interrupting you. I'm
Yeah.
just going to give you a heads up about the time. We do have time, but we may speed up a little bit just to allow some time for potential further questions from the audience. Thank you.
Okay. Yeah. I'm actually like very close to the end of my presentation. Yeah, so some of this is kind of like a detail showing what level has been happened, and I'm probably going to skip some of the slides here. And this slide is trying to show the switch on the fields is happen kind of like a quickly and determine the like data mining the faults and isolate the fault quickly, and rows are like within the design. So this is like the conclusions and recommendations based upon some of the events happen on the field and some of the lesson learned. One is that the battery and the microgrid is able to pick up the customer as designed, and it greatly improve the customer interrupt index. So this kind of like calculates how much is improve the system performances. And also one of the things, like I mentioned before, during one of the events, and we find out there was some like a difficulty synchronizing the battery island back to the grid because of the unbalanced, and also the tap has been stuck at one of the voltage regulators. So that kind of like a delayed the synchronizing back to the grid for the BESS. And the other one is when we trying to like charge the batteries, I think the charging one of the charging rates has been kind of like set probably too high, and the point of interconnection recloser was opened, and sensing the load is too high. So there is some like optimizations and more trainings with the operators need to happen. So that's all. Thank you.
Thank you so much.